So I live up in the Pacific Northwest of the United States, and as such, I get a lot of opportunities to hike around. And these days it seems like everywhere I go, I encounter stacked stones, people figuring out how to balance the load of multiple rocks on top of one another to create this kind of zen-like balanced feeling. And we want NSX to find its zen too. And our distributed switches have a policy, a teaming policy that is used to configure load balancing to support our VMs. So let's take a look at how we're going to configure that. So we want to look at teaming policies here in the vSphere web client. We'll head over to the networking tab over in the navigator, and we can see we've got two distributed switches right here. Let's expand out that compute switch, and of course we can see all of the various different port groups that are within it. So let's select D port group here as an example. We'll right click and choose Edit Settings. And in the Settings dialog box over here on the left-hand side, we can choose the teaming and failover. So we have a distributed switch. In this example, the distributed switch has 4 uplink ports that are by default all active, meaning that it will allow for load distribution, not true load balancing, but load distribution based upon some prerequisite property here. So we can see right now it's routing based upon the originating virtual port. So if I've got a VM, it has a particular port going into that particular distributed switch port group, in this case D port group. So another VM going into that same port group will have a different port into the distributed switch. And so when traffic flow occurs, it's going to be automatically distributed to different active uplink ports that are available. But what if instead of that we choose one of these other methods? For example, route based upon the source MAC hash. If we do that, then it's going to be very similar, but the switch is actually going to examine the incoming MAC address from the VM in order to determine how to distribute that traffic. And when a different MAC address from a different VM comes in, that will be distributed as well. Now, why would that be relevant? Well, because there are some services that are actually going to have multiple MAC addresses associated with the same VM, or we might have a nested situation of some sort of service. And so in that case, even though it's going through the same port, traffic with a different MAC address would also be distributed. But it's more work for the distributed switch to perform, which lowers the overall efficiency of the service. Now, another choice would be to route based upon the IP hash. Notice how broad that is. When we looked at the MAC hash, it was specifically the source MAC hash. When we look at the virtual port, it's the originating virtual port. But this doesn't say source or originating, it just says IP hash. And that's because this particular option will distribute the traffic based upon the virtual machine's source IP address plus the destination IP address combined together into a single numeric hash value that will then be used to distribute traffic. Therefore, if the same client is sending or receiving traffic and has the same source IP but then has a different destination IP, that's going to generate a different hash, which will then trigger actually delivering that out to a different destination uplink port. This involves even more work on the part of the switch to perform these actions, but definitely gives us a great way to allow for distributing loads, especially when we have VMs that are servers that are receiving a lot of destination inbound traffic, and as that traffic goes back out into the network, we want that to be spread as efficiently as possible. If we route based upon the physical NIC load, we're really doing something very similar to the originating virtual port, with the difference being when distributing traffic and one of these particular uplinks is starting to exceed 75% usage compared to the other interfaces that are available as connections, then the load will be distributed. So with this concept, instead of rotating between one adapter and the next, simply based upon the originating port, it may skip one of these particular adapters because it's already so busy. Now, all of these options are independent of the physical switch, but coordinating those decisions with the switch is possible if your switches are configured to support protocols like Ether Channel or LACP. And just as a quick reminder, the Link Aggregation Control Protocol represents a more sophisticated way to perform load balancing between ESXi and the physical switch uplink. With the built-in load balancing that's available between ESXi and a switch, we can support ESXi being aware that these ports are going to work together as a unit. But what about the physical switch? It has no idea that ESXi thinks of all of these ports as being equivalent to one another. So our load balancing is being controlled only from one direction. So ESXi has to do the thinking in order to choose the particular port that a packet will go on. Later, when a MAC address is received by the physical switch and it has to return that traffic, it'll choose the same port. But what about when the physical switch receives that BUM traffic, broadcast, unknown unicast, or multicast? Since the switch doesn't understand that these 4 ports work as a unit, it's going to forward that traffic across all 4 of those ports, wasting valuable bandwidth. So what would really sweeten this deal would be if both endpoints recognized that we were working with a bundle of ports that needed to function as a single unit of work. And that's what LACP does. The 2 devices will negotiate the number of ports that they're sharing and agree that they're working with a bundle. Not only do we get load balancing going out from ESXi, but we get original load balancing going into ESXi as well, including with regard to BUM traffic. This will also improve the response time in failover situations and even allow for things like a hot standby solution where redundant ports can kick into play if one of the normal ports expires. Let me cancel out of this configuration and show you where we go to configure that. If we head up to the switch itself, we can go to the Configure tab, and there's a setting for LACP. So if we click the plus on this side, we can see we can create a link aggregation group. We can associate it with a certain number of ports. If we are passive, that means we are waiting for the switch to determine if we are going to perform link aggregation. If we choose active, then we will suggest to the physical switch, hey, I'd like to perform link aggregation. Can we do so? And then we can choose our load balancing mode. So we could load balance the traffic per source ID, per VLAN. So all the traffic from one VLAN will go on one interface. All the traffic from another VLAN will go on the other interface, since we have in this situation 2 ports. We could divide it by the source and destination. Notice it's never just source only here. MAC address, if we want to look at layer 2 information. But that's pretty much irrelevant if you have to go through a router, because routers are all going to have the same destination MAC address. So it doesn't do a lot of great load balancing in that situation. But if you have a lot of localized traffic within the same subnet, that may be all you need. We could also look at it based upon the source and destination TCP UDP port and create a hash based upon service connections. So all the same type of traffic with a particular service would end up being routed into a particular NIC. We also have the source and destination IP address as a hash, but it also includes the VLAN. So it's now load balancing, looking at the VLAN and looking at the IP addresses. And then source and destination IP address, TCP, UDP port, and VLAN. This is going to do the most processing, but also give us the tools for the most granular level of load separation. And you'll notice that that actually was the default in order to ensure the greatest level of granularity. Now we're going to leave it with the defaults here and click OK. Now we have a lag group, but we're not using it yet. If we want to actually start using it, we've got this great link here, migrating traffic to our link aggregation group. Click on that link. So the process that we're going to go through involves opening up the port group and assigning the lag as a standby uplink so that it can be used for failover. Then we'll reassign the physical adapter to the lag port. That means we're unplugging it from the active port and plugging it into this lag port, which was standby. Well, now it's going to kick into being as a standby port. Then we can go back into the port group and remove those active uplinks, that's step 3, because they're no longer needed because they're not connected to any actual adapters. To see what that looks like, let's click Manage Distributed Port Groups, head to Teaming and Failover, select our distributed port groups, and for example, we can select this example D port group here, click OK, like that, click Next, and under Teaming and Failover, there we see our lag 1, and we remember we want to bump that into the standby position. Then we'll click Next, and OK. We only want to be in this situation for a short period of time. Then we go to reassign the physical adapters of the host to the lag ports. We go to Add and Manage Hosts. We want to manage our host networking on this distributed switch. We'll click Attached Hosts. Select 1, 2, and 3 here. Click OK. We can use template mode though to quickly modify the settings. Then we'll click Next. Pick host A as the template. Next. Then we can move VM kernel adapters and machine networking as needed. Next. So let's go ahead and select VMNIC 0. Click Assign Uplink, and now we can assign it to one of the lag ports that has been added. Click OK. Select VMNIC 1, assign the uplink, Select the lag 1-1. OK. Perfect. Let's apply to all so that all of our devices are consistent. Then click Next. None of the kernel adapters were on that particular port group, so we don't need to worry about moving those right now. So we can just click Next. That's not going to affect our iSCSI networking. Great. We'll click Next. Now, do I need to move any VMs on this port group? Well, if I already had devices connected to a particular port group, I haven't changed what that port group does. I've just changed how the interfaces function because now they're using LACP. So there's really no need to reassign VMs unless I specifically at this time want to migrate some VMs over now that LACP is configured, in which case it's just a matter of expanding the Twizzle next to a VM, selecting that row, and reassigning the port group to the port group you've just configured. Then click Next, and we're ready to finish. Once that operation is complete, then we can go back to managing the distributed port group, head back to teaming and failover, click Next, select our distributed port group, in this case of D port group, click OK, click Next. So what do we need to do now that we're here in teaming and failover? Well, lag 1 is no longer a standby. It needs to be the active uplink, and uplink 1 would be unused. Uplink 2, unused. 3 and 4, unused. There we go. Then we click Finish. And then we can close that Managing Traffic dialog box. It was just a very handy little wizard to jump us to the key locations where we need to make modifications. Now, let me just throw in 2 little wrinkles to this. Number 1, be consistent across the various different port groups that you have. Figure out what sort of load distribution algorithm you're going to be using and stick with it. If you don't, you get odd behavior. You can have switching and routing errors. So be consistent with your choice there. Number 2, VXLAN communication is based on the power of a VTEP, a VXLAN tunnel endpoint, where every ESXi system essentially needs to have an adapter that is an endpoint to be able to go onto the switch and or the routers and be able to work through other switches and eventually get to another ESXi service where we can de-encapsulate. So the VM kernel interfaces that perform VXLAN encapsulation and de-encapsulation are called VTEPs, VXLAN tunnel endpoint. And normally, if I have a VM kernel adapter that is bound to a port group that has 4 physical interfaces, that still creates only a single VTEP. But if we choose to perform load distribution based upon MAC address, then when I have 4 physical interfaces connecting ESXi to the switch, it will actually create 4 VTEPs, 4 tunnel endpoints. That means ESXi will actually have 4 different IP addresses to support the same service, and our controller will see that almost as if it was 4 different ESXi hosts that are providing NSX services. And down the road, that's going to be very important when we're trying to troubleshoot, to recognize that seeing all of these tunnel endpoints doesn't necessarily mean that there's that many ESXi hosts. It just means that there are that many different interfaces. Personally, I tend to be a fan of IP-based deliveries, especially using link aggregation control protocol when possible. So if that's an option, you won't see that, and it will just be 1 VTEP per ESXi host. Well, my friend, by going through this nugget together, you had a chance to learn exactly where the properties are for load distribution, and how to configure them in our port group level, and how to enable LACP if you've got physical switches that you can interact with using LACP 1 or 2 or Ether channel, so that you can get the best utilization out of your hardware in addition to the virtualization you're creating here in software. I hope this has been informative for you, and I'd like to thank you for viewing.